In this video, I'm going to assign S or R configurations to each stereocenter, and I'm also going to label each molecule as chiral or achiral. So I'm going to start with this molecule, which has two stereocenters, which are here and here. And we know that they are stereocenters because they are atoms that are attached to four unique groups. So the first step in figuring out the configuration is to assign priorities to the groups. So I'm just going to redraw this so my original molecule stays legible. And the priorities go by atomic weight. So bromine is going to have first priority. Hydrogen is going to have the lowest priority. And between these two carbons, this carbon is going to have priority because it's attached to a bromine, whereas this carbon is attached to oxygens, and bromine has a higher atomic weight than oxygen. So I guess I should note that this carbon, so even though it's attached to two oxygens, it doesn't matter. All that matters is that bromine has a higher priority than the oxygens. So this carbon will give the number 2, and then this guy gets 3. So what you do now is you place the lowest priority group in the back, and then you kind of count from 1 to 3, and based on the rotation that you get, you can assign the stereocenter either an S or R configuration. So for this one, we go from 1 to 3, and as you can see, that is a clockwise movement, which means that the stereocenter is in the R configuration. And I'm just going to do the same thing for the stereocenter on the left, where we have bromine is going to be priority 1, hydrogen 4. This carbon is going to have a higher priority than this carbon because it is attached to a bromine. So that's going to be 2 and then 3. And for this stereocenter, we're not lucky enough to have the lowest priority group already facing the back. So what you can do now when you end up in this situation, when you're doing these problems, is you can either redraw the whole thing, or you can just kind of rotate the image in your head and figure it out. But an easier way that I always did it is you just you figure out the rotation going from 1 to 3, figure out whether your answer would be S or R, and then just take the opposite of it. So for this one, we're going to go from 1 to 3, and that is clockwise, which would give us an answer of R, but we did it the weird way because the lowest group was facing us coming out of the page instead of going into the page, so our answer is actually S. So this stereocenter is actually in the S configuration. So now for the second part of the question is we need to decide whether the molecule is chiral or achiral. It's not enough to just see that the molecule has stereocenters in it and then say that it's chiral, because there's such things as meso molecules, which is a meso molecule has stereocenters, but it is still superimposable on its mirror image. So it's actually an achiral molecule. And the way you can determine whether a molecule is meso is whether the molecule has a plane of symmetry. And this molecule is meso, and the plane of symmetry is right here. And I guess I'm just going to redraw this molecule because it's going to be easier to explain that way. So we have our carboxylic acid group, which I'm just going to put R. And what I'm doing is I'm just rotating this this carbon around that atom so that everything lines up and you can see that this is a plane of symmetry. So we have bromine and the hydrogen. There we go. And you can check that this is the same molecule as this, and this is your plane of symmetry. And here you can see that basically it's almost like if you only had half a molecule here and held it up to a mirror, you would get the exact same thing. And that's how you know that you have a plane of symmetry. And also, just like if you held it up to a mirror, your S would become an R in the mirror. So that's a quick way to check whether a molecule is in a meso or not. So Because it's meso, it's achiral. So now for the second molecule, it's drawn in the Fischer projection form. And there's an easy way to do these too, which I'm going to do right now. This only has one stereocenter right here, because this has two hydrogens, so it can't possibly be a stereocenter for this carbon. Bromine's going to have first priority. Hydrogen's going to be fourth. Carbon attached to oxygen has priority over carbon that's just attached to a carbon and two hydrogens, so 2 and then 3. And when you're doing the Fischer projection, and you need to figure out whether it's an S or R, you need to have the fourth priority group, the lowest priority group, in the top position. And there's a quick way to do this. You just switch these two, and you also switch these two. And that way it stays in the same configuration. If you ever have a problem where you have a 4 on the bottom, you just switch the top and the bottom, but you also have to switch the left and the right. So for this one, we end up with 4 here, 2 here, 3 here, and 1 here. And then just like with these problems, you go from 1 to 3, and that is clockwise, which means that this stereocenter is R. And this molecule doesn't have any planes of symmetry as far as I can tell, so it is a chiral compound. Now for this molecule. For this third molecule, we have two stereocenters, which are here and here. This carbon is not a stereocenter because these two carbon groups have the exact same priority. As you can see, when they go around, they're attached to the same number of carbons. So let's start with this one. I'm just going to redraw it like I've been doing before. Obviously, the hydrogen is going to have the lowest priority. This carbon right here is a tertiary carbon, so that's going to be the first. Then we have a secondary carbon and a methyl group. And we have the lowest priority in the back, which is good for us. And we can see that this is in the S configuration. And I'm not even going to bother doing this one because I'm going to spoil it for you and show you that there's a plane of symmetry right here. And this is actually a meso compound. So you can see that, just like I said before, like if you hold it up to a mirror and it looks like the same thing, you can do that with this right here. And just like if you hold up your left hand to a mirror, you see your right hand, we can see that this looks exactly the same. So we know that this is going to be an R in the R configuration. And I guess I'll just point out that even though with the way it's drawn, it looks like this is the hydrogens going off to the left and the methyls going off to the right, these substituents are actually in the plane of symmetry, like the hydrogen's coming out directly towards you, and the methyl is going into the page because it's in the tetrahedral position for this sp3 carbon. So this is also an achiral carbon, or achiral molecule running out of steam. And I guess I covered everything.